Hey, it's me, Destin. Welcome back to Smarter Every Day. So you are probably well aware of the awesome science that comes out of space telescopes, but what you might not be aware of is the awesome science that goes into making these things work. For instance, check out this NASA photo. These guys are working on the sun shield for the James Webb Space Telescope, and what I think is so cool about this photo is that this guy in the bottom right corner is my dad. You see, the instrument operates at about 45 degrees Kelvin, but you have all this heat from the sun coming from the other side. So what Dad's doing is he's using this 3D laser scanner to make sure that the sun shield is perfect to provide a stable operating environment for the telescope. Thumbs up for you, Dad. I'm proud of you. So I thought I understood how space telescopes point at what they want to observe, but it turns out it's a little more complicated than I thought. I'll explain two ways that you can apply an external force on the satellite and get it to turn. First up, rockets. Okay, now that our space telescope is on orbit, how do we point it at a star? Rockets are cool, but they use fuel, which clouds up the area around the satellite, and you can run out of fuel, ending your mission. So how do we do this without having rockets? Hang with me on this one. Think about this little compass needle. It's interacting with the Earth's magnetic field, but what if we scale it up and create a big needle, like a rod or torque rod, and we put a coil of wire over the top of it, and then we take this wire and we hook it up to this power supply I have on my desk and then turn on the voltage. See that? An electromagnetic field. So is it true that this electromagnetic field in my hand is interacting with the Earth's magnetic field just like this compass needle that we were able to get to rotate? Yes, that's exactly what's happening. So here's the deal. This is called a torque rod. Scientists do this all the time on spacecraft. They take 3 torque rods and they put them in 3 different axes, and they're able to apply or remove voltage as they need to rotate depending on where they are in the Earth's magnetic field. Now this is a very elegant solution because there's no moving parts, but the problem is it only works in places where you have an external magnetic field, like Earth. This wouldn't work in deep space or even on Mars where you have a really low magnetic field. So in order to rotate a space telescope somewhere like that, we're going to have to use flipping cat physics. So if you go back to the last episode of Smarter Every Day, I used a high-speed camera to explain that a cat is able to flip 180 degrees from rest by rotating against himself. Go watch that last video if you need a refresher. But what I didn't explain is that this ability to change the overall state of the system without violating the conservation of angular momentum is a very special problem that's been studied by applied mathematicians, neuroscientists, robot builders, and even astrophysicists. Just do a quick academic search for flipping cats and you'll find out what I mean by seeing thousands of pages of equations. Okay, so to explain why cats are so special, let's get a block of wood with a hole in it and a ping pong ball with a mark on it. Then we'll mark the block so we can tell how the two line up. If we move the block, the ball rolls, and when we return it, the system goes back to the initial state. And this is always the case, right? Nope. If we move the block out but return it along a different path, the system doesn't return to the initial state. This means that the path determines the state of the system, right? So just like the ball never slips, angular momentum in both cats and space telescopes never changes. But we are able to change their final rotation. You see, special systems like this are called non-holonomic systems. Look, I know that's a big word, and you might just be watching this video because it's a cat video, but I need you to hear this. The physics of flipping cats is what makes us be able to take photos like this. No, seriously, flipping cats. One way to keep a space telescope pointed at a particular star is to use a device called a reaction wheel. Multiple reaction wheels are spinning inside the spacecraft. If a rotation is needed in a particular axis, engineers calculate which wheels should be sped up or slowed down at exactly what times. So I am in a NASA building and we are going to a special lab. We are here at the Attitude Control Components Lab, and these guys know about how to control space satellites using cat math. Here's our guide here. Come on in. Okay, Dean, so thank you for allowing me to come over after I showed you my cat video.
That was pretty cool.
I appreciate that. So I have a question. So a cat is just free floating in space essentially, and then he rotates.
Correct.
How does he control his rotation without any external forces on him?
Well, he basically uses his legs and his body to rotate and have momentum transfers.
Oh, and that's kind of what you guys do, right? You're brokers of momentum.
Yes, we do momentum management. That's what happens on the space station or any system that's flying in space. Is we have to manage the amount of momentum that's actually in the system so that you can point and focus at a nebula or a star that you want to look at for a telescope.
And so what is this device that you have next to you?
Well, this device is a control moment gyro. Now the difference between a reaction wheel and a CMG is in the CMG I can actually rotate its axis. And you can see this actually has 2 axes of rotation. And by doing that...
you made a lot harder math for yourself, didn't you?
Yes, we did. But there are a lot smarter people than I am that go off and make sure that they know how to point the satellite or the telescope, and they go from one point to another point along a specific trajectory. But if I keep rotating this up, you'll see that there's a point where it will stop. And if for some reason I were able to get to this point, then I can't go any farther. So I have to have some other system to allow me to get out of that locked position.
Oh, so that's where your external energy inputs start coming into effect.
That's right. That's where your mag torquers or your propulsion jets or thrusters.
And the torquers would be the Earth's magnetic field.
Yes, you react against Earth's magnetic field.
Okay, so here you guys test the components to make sure that these things will work on orbit.
Yes, we do. And in this vault over here, you'll see we have a life test running.
Is that what I'm hearing here?
That's what you hear.
So what am I looking at?
This is the Chanda X-ray telescope life test for the reaction wheel. And what we're doing is we're testing the systems to see how long it will last, so that if there's a failure on, say, the wheels, then we can go in there and say, we can take the wheel apart.
I noticed you have a really old computer running this thing.
Yes, well, Chanda was built in the early 90s, and so the hardware that is used to test Chandra is the same hardware that is flying on Chandra. So you got to remember that Chandra is now about 13 years old, I think.
Oh wow! So it's like you're locked in time.
Yes.
When you launch the thing, you're locked at a certain time, and you have to continue to use that same hardware.
That's the same thing you had the problem with the space station, or the shuttle. They were locked into time with the components that were built way back in the 70s.
Thank you very much. Appreciate it.
So thank you very much for watching. I hope you learned something about cats that you didn't know, and please consider subscribing and sending this to your friends. Gigi, get it. Get it. You hear a bird? You hear a bird?
We had a ball. The only reason you can do this is because it's a non-holonomic system and you know flipping cat math. Okay, I'd like to thank Jimmy Neutron for the use of his farm and his cat.